So like we had mentioned in the initial video, the first video, FFT stands for fast Fourier transform, and I said it is a faster way of implementing DFT by reducing the number of computations. So let's see how this computation efficiency comes along. So basically we have to look at how it becomes faster, and when we look at this particular operation involved, we can see that there are two kinds of operations involved. One I refer to as a complex addition, and I refer to as a complex multiplication. So let me write it down: complex addition and complex multiplication. These are the two operations involved in these operations. So to implement a butterfly, we see that these are the two formulas: a plus b wnk and a minus b wnk. So in implementing a butterfly, which is given by this formula, we can see that there are two complex additions. I mean, if this is multiplied together, it is it's appearing in the next term also. So since that is a particular case, there is only one complex multiplication happening. But meanwhile, you can see that there are two complex additions happening: a plus b wnk, and here it is a minus b wnk, which can be treated equivalent as a plus minus b wnk. So essentially, when you look at this implementation of one butterfly, you can see that there are two complex additions and one complex multiplication happening. So we saw in our particular problem that we did just right now, we saw that we implemented 4 butterflies: 1, 2, 3 and 4. So over implementing 4 butterflies, we can see that for one butterfly, since it requires 2 complex additions and 1 complex multiplication, for implementing 4 butterflies, we have to use 8 complex additions and 4 complex multiplications. Now let us take a look at how this is implemented using this particular formula of DFT. So you know that formula of DFT is x of k is equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi n k by capital N. So when we expand this for one particular x of k, x of 0 into e raised to minus term plus x of 1 into e raised to minus 2 e raised to minus term plus x of 2 into e raised to minus term and plus x of 3 e raised to minus term. So this makes up one equation for a situation of a 4-point DFT. One equation for a computation of 4-point DFT. So when for one equation itself, we can see that there are 4 complex multiplications happening at here 1, 2, 3 and 4. So there are 4 complex multiplications happening and 3 complex additions: 1, 2 and 3. You can see that for implementing one equation or for finding one answer of the 4-point DFT, we require 4 complex multiplications and 3 complex additions. So finding 4 answers will result in 16 complex multiplications and 12 complex additions. So I have put up a tabular column over here for a 4-point DFT, and using this particular tabular column, we can understand that when we do it using the formula method, complex multiplication required is 16 and complex addition required is 12. And when we look for FFT, the number of complex multiplication required is 4, while complex addition is 8. You can see that the number of computations have been reduced in this particular case of FFT over DFT. Now, in general, we can write it as a formula like this. Now here n is 4 here. So collaborating these equations, we can write the table as follows. So for a DFT operation, the number of complex multiplication required is n square, and for complex addition required is n into n minus 1. Now in FFT, the complex multiplication required is n by 2 log of n to the base 2, and complex addition required is n log n to the base 2. So I have just compared it for the 16 case when n is 16, and when we look at n is equal to 16, we can see that n square will result in 256 complex multiplication and 240 complex additions in terms of your DFT computation. And meanwhile, for your FFT concept, this complex multiplication required is 32. So when n is 16, n by 2 here becomes 8, and log of n to the base 2, log of 16 to the base 2 essentially means if log of 16 to the base 2 is m, what it essentially means is that 2 raised to m is equal to 16. So here m is 4. So n by 2 is 16 by 2, which means 8. 8 into log of n to the base 2, 16 being here, it would be 4. So 8 into 4 is 32. And you have n log of n to the base 2. So n is 16 here, and you have 64. So these are the number of computations required for this particular operations, and you can see that again the number of count is significantly reduced. Imagine what would be the case of a 1024 situation. So when it comes to 1024, one could find out the answers using the calculator. You may try it on your own and see what is the difference in the number of computations. So the last topic in this section would be the computation of percentage in computation, percentage of saving in computation. So we have to see what is the kind of savings that happen when we compare DFT with FFT in terms of number of operations. So complex addition is there and complex multiplication is there. So we use a formula, number of CA in DFT minus number of CA in FFT, whole divided by number of CA in DFT into 100 to 4. So we have taken the case of computational efficiency for n equal to 16. So in that case, you can see that there is a saving of 73% in terms of complex addition and 87.5% in terms of complex multiplication. So that is what happens in this particular case, and I hope the topic is clear.